Okay, so we took some time on Monday to look at a lot of the theory behind the convolutional neural networks to understand the principle behind how they work, to understand the whole idea of convolutions, the whole idea of filters, the whole idea of kernels filters, and the spatial um, you know feature the features, right? And then we also looked at the whole idea behind it, the thinking behind it. We looked at the different components of convolution layers, which is made up of a conv 2D layer. So we are going to look at that when we are doing this hands-on. And then the whole idea of convolution itself, right? Which you could actually summarize it in a few things, right? Um, the spatial structure, the hierarchical features, right? Then solving depth and efficiency challenges, especially in the more recent designs or architectures of CNNs that used the skip connection, what we now call residual networks. Okay. And then we also talked about transfer learning. We'll do a little bit of example on transfer learning. So, yeah, so there was a whole lot of theory there, and I think I encourage everyone, if you did not really understand or get that, you can still go back and go through the video, right? Those theoretical concepts are very, very key for you to understand what to do with when you now get to the hands-on of trying to use convolutional neural networks when you are doing, model training, or you're trying to design a model, or you're trying to do anything that has to do with CNNs. Remember, CNNs are really performance designed for image task. Okay, so one of the um, basic image data sets that are used to assess or classify how good um, neural networks are in image task is the MNIST. So the MNIST is a data set that contains handwritten digits in different shapes and forms, orientation, and all of that. That's the training data. And then, of course, at the end of that training data, you have one column that contains the classification. So that classification is the digit. Normally, MNIST comes because these are images, right? You cannot have them in a table. So you're not going to read them with, you will not read them with pandas data frame. This is not a table or a CSV file. These are actually images. So the way it is normally structured is that the images are stored in different folders. They are stored in different folders. And then each folder is labeled in such a way that from where it is saved or the name of the folder, you it tells you the classification, whether it is um, digit 0, digit 1, or digit 2. So there are actually 9 classes, 0 to 9, each of them representing which digit was written. These are, of course, English, Latin, and the Arabic digits, okay, not any other language. And those images are grayscale. In other words, they are not color images. They are, I wouldn't say black and white, because black and white means you only have two scales. Either it's totally black or totally white. But grayscale is where you have different shades of gray in the images, right? So what that means effectively that when you are converting those images, you know, to a data set that contains essentially the NumPy array that contains that, what you are getting is a list of numbers, right? A multidimensional array of numbers where there's actually you can decide to do it 2 by 2. Well, sorry, 2 dimensional is what I wanted to say. You can have 2 dimensional, right? And then there's no third dimension. Well, there's a third dimension. The depth is one, right? That one is just the um, amount of black, or how black that particular pixel is. So that's the data. So we are just going to go hands on, and we'll look at how that works. Then we'll come back to transfer learning. We'll look at the principles behind transfer learning, and then we'll come back and do a bit of hands-on transfer learning. So let me start first of all just by giving us a little um, you know, um, insight into images, right? Because for you to do image classification, you really need to understand how images are represented. I've actually said that already, but I want to demo it, okay? And um, one of the interesting things is you can manipulate images directly at the pixel level. Most of the code that you would write, they don't show you how you can manipulate images directly, because most people don't need to manipulate the individual pixels in an image, right? But um, in this case, because we are training models, it is a good idea to know how to do that, right? It's a good idea to do that. And it's very easy to do that with Python. With Python, you have the PIL library, right? The PIL library is a library that you can basically open an image. And when you open an image from a file, it actually converts that image into, you get the original pixels in that image. And then you can, you know, um, play around with it, right? So we're going to do a little bit of those PIL operations. Okay. So first of all, you have to import the PIL library, right? That is the entire thing is called Pillow, right? That is the name. It is called a Pillow, right? Typically in your Jupyter notebook, uh, it will be there, but if it's not there, then you install Pillow library. So this is how you start from PIL, which is the name um, in Python, right? You can import an image object. So let me try first of all to see if it is here. If it is here, good. If it is not here, then we will pip install Pillow, right? That is required. All right, so it is here already. It's already part of Collab Notebook. Now let's get an image here, right? So I can look for some sample images and just download it. The sample data here, interestingly, in your Jupyter notebook, if you look at it carefully, you will actually see there is some sample data that includes MNIST, test and train, right? Which we can open and look at, even though I'm not going to use this one, right? But um, this contains the same kind of data, really. So in the MNIST test and train, the images have already been loaded, and basically they have been converted into number values and maybe stored in a table. So you can see it here, right? I think they have been normalized into um, integer form, right? Um, and that's an interesting thing. So you have, I think this is even like a pixel row column kind of thing, right? Where each of these numbers represents the number of um the degree of whiteness, right? So basically, if you look at this, a zero value here, I guess this CSV gives you um X, Y. It gives you in two-dimensional form. So it's actually two-dimensional. The way the pixel itself would have been. If you look at it, you will see that where the image is dark, the value is zero. But where the image is bright, right, where the pixel rather is bright, you have a number. So the higher the number, the brighter the image. If the number is 254, that's the highest number because this is in using an ASCII range. So basically, if the number is 254, that means that's white, right? And if it is lower than 254, it is gray. And you have different shades of gray, including very almost black variants. So that's how images, this thing gives us a very good idea of how images um, are organized. Let me see if I can make this a bit larger so that we can really see what it looks like. So let's see. I can expand this, even though it has only given 10 per page, so it's only 10 rows. So you cannot see the entire thing, but there are there are 9,999 entries, right? Um, yeah, so okay, this might mean the number of images actually, right? I need to confirm that they are that's the number of images that we have. So each of these represents the image. Okay, that's true. Each row represents a separate image. So this is not two-dimensional as I thought, but it is flattened out version of that image, right? It's flattened out. Uh, so yeah. Then the column at the beginning is you can see it's a label category column. Basically, this label represents a category of that this image represents. So remember, each category actually just maps to a number. So if the label is 0, that means the number that these pixels represent is number 0. If label is 7, that means the number that these pixels represent is number 7, and so on. Well, that's how this is structured. But if you get from PIL, now I'm going to um, play around a little bit so that we see what happens with pixels and so on. The MNIST database is made up of very low resolution images, right? Because they are low resolution images, it means you can actually even pick out one single pixel, do something to the pixel, and you will even see some effect. So let's start off. If you want to load, PyTorch comes with MNIST. PyTorch dataset comes with MNIST already. So you don't need to go download it elsewhere. We could have downloaded it elsewhere anyway. We could go to Kaggle, for example. You can go to Kaggle and search for MNIST dataset, and there are a lot of it because there are a lot of this is like one of the basic things traditionally in machine learning that people use. So, for example, this one, um, this actually contains 54.95 megabytes. I'm sure if you take any of these folders, um, you can get images from this and you read it in a particular format, right? So but let's just use what we have in PyTorch. So the first thing is let's get PyTorch in. I'm still going to show you how you can manipulate images with PIL. As a matter of fact, let me just get a very low resolution image, right? Which I will show you. So it's easy to do that. You can just search for a low resolution sample image from the internet, right? Any random low resolution. These are not actually low resolution images. They're pretty high resolution, actually. Um, okay, Kaggle has a few, right? Um, these are still not low resolution, but these are in JPEG format. So let's load this one, right? We'll have a data set of this, which we can then take and we play with. Okay. Um, so I'm going to essentially take this. Remember when you are trying to download dataset from Kaggle, take this after the data sets here in the link, take the last two. The first one is the person's name, the owner of the data set, and then this is the name. So this is similar to what we have with GitHub. So we will now let's get the Kaggle Hub, import Kaggle Hub as KH. Okay. So to download this, so we'll call the Cargo Hub dataset downloads. Okay, so we have to download the dataset first, and then you specify the cargo um you know the cargo handle here. That's all. Then when you download this, right, this path is going to contain the path in this Jupyter notebook where you can find that. So you can do a bit of trying to figure out where things are and all of that. But I think the fastest way is for you to just go here to the original place and then check the folder structure here. So here you see the folder structure by the right, at this right sidebar. You see that there's a folder called dataset. And then inside that folder, this data explorer is what you use, not summary. Summary gives you a summary of the images. Okay. The types of images. But here you can see that there's a folder called dataset, and then there are images that are named from image one to whatever. So that means the path, the full path that we'll have will be image path would be the path, right? Which is what we downloaded here. Okay. Um, which is the path where this download happened. And then you can add concatenate to the it data set, which is the name of this folder here, right? So that's how you do that. And then we can now decide to pick any image. Maybe let's say image one. Okay, so that's the one we will start with. Okay, so but we have the image path. Now to load an image with PIL is actually very easy, right? You simply do um you simply do image.load, right? It's as simple as that. You don't need to do much more than that. Image.load. It's enough. Okay. Once you do that, then you have um um image dot open actually. So the actual image will be image dot open. Okay. You specify the file name. So in this file name is image path. That's a full path, to that image. Then the name, because remember this full path ended at data set, but we still need to add the image name. And if you look at what we have here, we have image one, image 10. This is actually different images starting from one to, how many. We can actually write some code to inspect all of that, but let's just go with image one dot JPG. Image one dot JPG. So PIL can load different image types. It can load PNG, it can load JPG, and so on. So that's it. You've gotten the image. Now, if you want to see the pixels, you just use image img.get data, right? That gives you, yeah, it gives you this. Now I have to convert it to a list. Okay. So let's convert it to a list. If you want to convert it to NumPy, which is what typically you would do. So when you get data, you can see this gives you um, three. It actually gives you a triple, right? It gives you triples. That's how PIL does. It gives triples. The triples are made up of the triples make up the RGB values. The amount of red, the amount of green, the amount of blue per pixel. So this defines just one pixel. Okay. As it turns out, this image is actually quite large, right? If I check the number of pixels, you can easily check the number of pixels in the image by doing something like this. The length, you can do the length of that list that we just did now. Okay. So this gives you the number of pixels. So you can see 748544. Now, you could also decide to get a pixel value at a specific coordinate. So remember, images are row and column. So you can get the image value as at a particular pixel by image.getPixel. Okay. And then you specify the pixel location as a tuple. So pixel at x is 20, right? That's the 20th pixel from the x axis. And then from the top axis, the 40th pixel. Okay. That gives you the pixel value. So that the R is 213, the G is 202, the B is 174. Okay. Um, then the other thing you could do is if you want to print the image, right? To print the image, there is very simple way you can do that using Matplotlib. You typically use Matplotlib if you want to print images in um, you just take the image data and you plot it like a graph. That's how simple. Well, yeah, that's a simple idea, right? That's a simple principle. You take the image, right? You plot each pixel value. You provide the pixel value as the value of the color, right? And then you plot it. So that's how you do that. So sometimes it takes a bit, okay? But let me show you how to do that. Um, the first thing is um okay, so first of all, you import matplotlib. So from import matplotlib dot pyplot as plt, which is normally what we have been doing since. Yeah, it should be import, not from. So you import matplotlib, then you create a kind of image canvas, right? Alternatively, you can just use plt.image_show, which is pretty simple. Matplotlib already has a built-in image um, plotting, method, right? So if you look at this, you even see that there are two ways you can specify the image. You can specify an array, which is a two-dimensional array, or even a single vector that contains the image data. Or you can even plot an image object, which is what we just got from Pillow. You can directly pass in a Pillow image object and to plot it. So let's see how Matplotlib does that. So I can just do img, which is a Pillow object, the image object. Okay, so you can see it has plotted it. Now, if you look at this image, you will see that this image is not entirely grayscale. There's a bit of yellow colors in it. Okay. And if you look at it, one good thing that Matplotlib does when plotting images is that it allows you to see the number of pixels. So you can see that you have 1,000 and something pixels here and 600 and something pixels here. So if I wanted to grab the pixel right here, right? The pixel right here is at X 400, okay, and Y 400. That's a pixel at that point. So let me draw it as a line so that you can easily see. So if I want to grab the pixel at X equals to 400, right? And Y equals to 400. So if you notice, you see that Y is counted from the top down. In images, the origin is actually at the top and it goes downwards, unlike normal graph plotting where the origin is at the bottom. That's the Y origin. The Y origin in images is normally at the top. But in normal graph plotting, the Y origin is at bottom and goes up. But here it's at the top and goes down. Well, that's because there are no negative numbers in an image, right? There's no negative coordinates in an image, right? Image coordinates are always positive. And then, but the X always starts at the left as usual and goes rightwards. So I can now grab, if I want to grab the pixel at this point, that's what we were saying, get pixel. And then, so you can just say image.getPixel. and 400 by 400. Okay, 400 by 400. You see the value. So you can see the value 136,119,109. This is a very high value, meaning that it's almost a white. Well, okay, it's not white, it's oh sorry, I did not draw the second arrow well. This is not 400, 400. Um yeah, 400, 400 is almost a white pixel, a white colored pixel. But it's not very white. It's not perfectly white. The interesting thing is you can actually change the value of a pixel, in a PIL image. You can manipulate the images. You can change values, right? So for example, I can actually change the value of a pixel, and see if it affects it. Okay. So you're likely, you're going to use, you know, um, you can use data, okay, and then you specify, right? Um, um, you can just specify the pixel location, okay? Um, um, so let's see. So you can get pixel. So I got pixel at 400, 400, and the value of the pixel is the R component, the red, the green, the blue component. I can now also change that pixel. So to change the pixel, you can use put pixel, right? You use put pixel. So at the same location, 400, 400, okay? But we'll specify the value. So the first tuple is the location where I want to put the pixel. The second tuple is the value. So let's assume I only want it to be red, for example. So I can put 255. 255 is the highest value you can ever give. 00. So this is RGB. So a color that is made up of all red, no green, no blue is obviously going to be red. So I would expect that at this point, right, it may be too small to be visible, but we'll see it. We'll still use the plot.imshow, image show, uh, and we'll see if that our red pixel shows up. It's actually very small, so you're not even seeing it. And that's to show you um, how tiny a pixel is. If you wanted to really make let me even just prove, right? We can try to get the pixel again after putting it, just to be sure that I actually put it in, right? Um, yeah, so you can see that. But the pixel is so tiny that you will not see it. If you really want to make a big enough size of change in the image for us to see, you would have to um, basically loop through a particular section, right? So let's see how we can do that, because one single pixel, like I said, the image is still a high resolution image. It's 600 and something width, right? By the way, I didn't even mention that that is the uh the dimensions of the image. So um yeah, so let's loop through, right? Let's loop through. So if you go through this, you have to loop through the Y side, okay? And the you get the height, which is image size. The image size is always specified. Oh, by the way, that's something I didn't mention. So you can get the image dimension using image.size. Okay, image.size will give you dimension. So you can see the X is always specified first. So the X pixels, the X pixels is 731, the Y pixel is 1024. You can actually see it here. That's why this is 731 and this is 1024. So that's the dimension of this image. Now you can take this image size and you can, of course, deconstruct it into the width and the height. Okay, which is what to now have the width. So we start with the height first, right? So you run through the height, but I'm not going to go through every single pixel, right? I want to go through pixels that are around this 400, 400. Let's say 400, 10 pixels to the right, 10 pixels to the left. Same thing for the height. So it's not going to be range of height, but rather it's going to be starting from, 400 minus 10, right? Let me call that the swatch size. The swatch size, which is the size of the section that I want to modify. So let's just say it's 10 pixels. So we'll now have width 400 minus swatch size and to 400 plus swatch size. Same thing for the X, right? Um, 400. X is also the 400 position. This is just for me. By the way, this is kind of a digression. I'm just trying to show us how to manipulate images, right? So that when you look at all the code that we are writing for images, it will not be too complicated for you. So I'm not going to do all of this complex stuff. All I'm just doing is put pixel, and I want to put 255,000, right? To make it, oh, you need to specify the location first, which will be X comma Y. And then you specify the value of the pixel you want to put, which is 255,000. So if we run this now, you now see that I would have put a a square. Well, okay, I'm surprised I'm not seeing that. So maybe the 10 is not even big enough. So let's try something even bigger. 100. Well, 100 should be big enough to be noticeable. I think we may have to reload the image. Um, yeah. Let me just look at this because I'm surprised that it did not make any difference to the original image. Get data list. Um, let me also find the position that corresponds to 400. So that would be 400 times image dot, if I let's say width, 400 times width plus um, yeah, 400 times width. Sorry, that should be 400 times height. 400 times height um plus 400. I just want to confirm something. Yeah, so it doesn't seem that the original image is affected. Um, so um, so let's create a new image. We can create a new image. I'm surprised because uh, if I do get pixel, I still get it. I get the correct thing, but the image itself doesn't seem to be affected. So So it has actually updated it, but okay, anyway. So I'm not going to dwell too much on that because that is this is just kind of an introduction. Okay. Let's try something. Let's try something. So let's I feel the original image is what Matplotlib is still printing. So there's a way you can retrieve the updated image, right? Because maybe as we are setting the pixel, it is not actually modifying the original image channel, just modifying a mask. But that mask is not what Matplotlib sees to print. So what we do is we can use NumPy. It's actually much easier if we use NumPy directly and modify. So all of this would have probably been nicer if we use NumPy. So let's use NumPy. So we import NumPy as NP. Typically, you actually use PIL pillow with NumPy before you convert into a NumPy array. And then the NumPy array that you can pass your into your um you can plot or you can print with uh um Matplotlib. So let's do NumPy array. So you can call that image arrays np dot array, right? As usual. And then you just pass the image in. Okay. Um, so we can also still check that image array. It's because it's not an array, you can get this location that I have here, which should still give me the should give me the new values. But let me just see in case I made a mistake. Okay, let's see img array dot ship first of all. All right. Okay, so this has three channels. Oh yeah, so I actually forgot. I only changed yeah, I changed the three channels, right? The shape is 1024. So NumPy is using the three-dimensional shape of this image. So let me explain why it's three-dimensional shape. The first shape is the Y, right? The Y axis, which is 1024. Okay. The second shape is the X, which is 731 pixels on the X. And then the third, or rather the first dimension is 1024. The second dimension is 731. The third dimension is the RGB. So that's why there are three. The first is the number of R, the second is the number of G, and the third is the number of B. So if I want to get that, so now we are going to use NumPy's approach of accessing it. So I'm going to do 400, which is the first dimension, and then comma 400, which is the second dimension. This should now give me a third dimension that has 25500. So this still has the pixel I had set. So I can now use pyplot imshow to print this. This should now carry, well, it does carry. So it looks like my changes were not large enough to be seen, right? But it's surprising. Um, Let me try 300, 300. Okay, so 300, 300. Um, yeah, so it seems like all I did was just change a single pixel, but this one that I did here did not seem to work. I don't know why. Um, Okay, let me try 350 and see. Yeah, it is still a single pixel that got changed. Um, oh yeah, okay. So there was a bug in my code. There was a bug in my code. The bug in my code was it only changed 1 pixel at 400 minus swatch size. So let's rerun this. So a very thin line is what was changed. So let's see. I think this time around we should have our red. We should have a red square. Yes. So this is what I was trying to show you that you can directly manipulate. And yeah, of course, that still works here as well, right? But again, a single pixel is still too small. I can still change the value in a particular piece of it. I had done 10 by 10 before, so maybe I'll go back to a swatch size of 10. Let me reload the image and do everything again. I don't really need to, yeah, I don't really need to run the whole thing, right? Let me run from this point down. So this was it changing this is the original picture. This is a 10 by 10 square. So anyway, I that bug, that was the issue. Sometimes that happens. Okay, so this is just to show you, give you a kind of grounding of how images are represented. The question you might ask is why was it red color? Because remember the images are always specified as RGB, so you mix the colors. Okay, so if I wanted an orange color, what are the two colors I would mix to get an orange color, right? Um, let's assume let me turn this into a function that I can use, right? And I can just call this function set swatch. So you specify the image, which is a pillow image. You specify the position, which is just an int, and then you specify the swatch size, um, which is an int, and we can give a default value of 10 pixels. So this is just so that I don't need to keep running this code all the time. So yeah, so every place here that is, oh, this position should be a tuple of string, right? So let it be a tuple of string. Um, um, Ideally, this should be written as tuple, tuple of int, int, and int. Okay. Uh, all right. So the first is the X position, which would be position 0. We always take the 0. We always take the X as the first, and then oh, this is Y. So Y is the second um is a second is a second dimension in a position 0. Okay. So think of this position as an array. It's just an array that has two values. That's what a tuple means, basically. It's an array that has two values. The difference between a tuple and an array or a list in Python is that a tuple is immutable. You cannot change its values, but a list is mutable. So a tuple, it has two values that are both ints. The first one is the X position, the second one is the Y position. So index 0 is the X position, while index 1 is the Y position. So since we are looping for Y position here, we have to pick from index 1 and then go to the left, or rather go up, start above it by 10. In this case, swatch size is 10. Go up by 10 pixels and then start from there to paint, to adjust all the pixels. You're basically painting, right? These are primitives, things that, graphic software do usually. But what we are doing is just, um, you know, basic stuff here just to show you how you can manipulate images a little bit, right? So, This is position zero. This is position zero. This is the again position where you want to adjust the zeroth coordinate. The zero dimension is the x coordinate. Okay, so and then we should also specify the swatch value. Yes, yeah, I forgot that. So let's put that here. Value. So that's the value we want to put. So again, this will be a tuple that represents x, y, z. Okay. So that should be int. So that's the value you want to set. Um, oh, okay. I should have written this way. Okay. So we'll replace this 2552550 with the actual value. Uh, so that is value. Okay. So we have a function now. Makes it easy, so I don't need to keep calling it. So I can still do I can set a swatch value now. Um, set swatch. Swatch is just saying a section of the image that I want to adjust. So I'll take this same image, peel image, and let's say the position now is maybe position 300 by 300. So if you look at position 300 by 300, it's going to be somewhere here, 300 by 300, somewhere here. So let's say I want to set a different color. Okay. So the color value is a tuple, which is RGB. So if I wanted it to be green, okay, that's green, blue. If I wanted it to be yellow, for me to get yellow, I mix, what are the colors you mix to get yellow? It's red and green. So if I put 255 in the red um, section and 255 in the green, that gives you a fully saturated red and green. Okay. Then after that, we plot it, we print the image. And you now see that you see the same image, but we've now added a yellow swatch up there. Okay. So this is how you can play with images and do all of that. So I was just trying to show you how you can do a little bit of basic image manipulation with there's much more you can do. So you can go and check out PIL. Another library you can also use apart from PIL that we convert to a NumPy array. You can directly, as you can see, you can directly set the pixels by using put pixel and get pixel. But if you want to use it for machine learning, you cannot directly use the PIL image that way. You have to convert it to a NumPy array, which is what we just did. When you just pass it as a parameter into np.array, right? So NumPy understands how to convert a peel image into an image array. And you can do the same thing. I could actually have directly made changes to the NumPy image by directly changing the pixels inside the array. So at least this gives you an understanding of what is going on in images. Of course, the question we ask is why is this one having so nice, grayscale colors? Yeah, we have to know what grayscale to use. I could actually do the same here again. Maybe instead of just using, um, you have to understand colors, right? And for those of you who have done a bit of, you can now mix, colors that are similar, right? If the three colors are the same, it will give you gray. If the three colors are the same. Now let me do this at 350 rather than 300. So I will see again how it looks like there. So you see it's here in the middle, right? It's now looking gray. So it is these numbers, how you combine these numbers that determine the thing. But this is in a gray scale image. Now let's go do the actual thing that we were doing, which is um load mnist. Okay. Now to load mnist, you use PyTorch. So let's import PyTorch. I'm not going to go through the entire thing, right? But I am just I'm just going to show you how to there's another notebook that contains all of that, which we'll go through it step by step. But PyTorch has the uh, library, import touch. It has the data set that contains MNIST. So let's just explore that a little bit. So you have touch vision, right? It is in touch vision. That's where those are. So from touch vision, you have data sets. Okay. Um, so now this touch vision, actually the data sets will be downloaded, into your system. One thing you can do, at how you pull data from PyTorch dataset. For example, the MNIST, you will use dataset.mnist. That's how you get that. So it's very easy. Okay, you just use datasets.mnist and you are getting its own um values, or the original images. Typically, MNIST comes as a folder. Okay, it actually comes as a folder. But if you are using PyTorch to load it, it does not come as a folder anymore, right? So for example, let's call it MNIST datasets.mnist. You can see they also have Cypher. If you actually check this, you see that they have Cypher as well. They have a whole bunch of data sets that are traditionally used for machine learning, either for training or for model evaluation, to know which are the best models for all of this, or just for learning, like what we are doing now. So you take MNIST, okay, it's a class. So you can then specify where you want to store the data. So typically, root is where you want to store the data. Let's just put it in /data. So this /data corresponds to a folder that will be created somewhere in this your um, workspace in the runtime. Now, train equals true allows you to pull training data only. If you say training equals to false, it will pull only testing data. So you actually have to run two different queries to get the train data or the testing data. Then download equals true means if the data is not there, download it. Then there's something else called transform. So we've not talked about this yet. Transform will be if you need to do some kind of transformation, right? Um, Maybe you want to convert it to tensors and all of that. But for now, let's just download it because we are just trying to see what is happening. So it downloads it, and you can see it downloads. It makes 4 downloads. The first one is the data set itself. This data folder, you can see it has created this data folder. And if you open it, it opens, it creates the MNIST folder. And then you have the raw folder that contain the raw info images. All right. If you open this, the raw images are here with this ubyte.gz and all of that. Okay, so it is storing it in a byte format. It's not a format that you can easily open. It's not really an image format per se, but it is a compressed format. So that is what has been downloaded. Now, you can then, this is optimized for PyTorch, right? The next thing is you can use a data loader to load the images, and then you can look at the different images, okay? Normally, how you use a data loader in PyTorch is to import the data loader class. So that is from touch.utils.data. Touch.utils.data. You import a data loader. So remember, we used data loader before with sklearn, right? So it's the same principle. Um, the the data loader in sklearn that we use allows you to basically take a whole data set, connect it to the data loader, and so you are loading batch by batch instead of the entire data set into memory. Because sometimes data can be large. Like this one now, the data is pretty large, right? So you don't want to start loading all of that into your memory and start training your model on it all at the same time, okay? You want to be able to load in batches. So the benefit of using a data loader is that it optimizes that whole loading function, right? And makes it efficient and fast. Because if you're loading all of them at the same time, it will be really slow. So you can now create a new data loader. You can call it MNIST data loader. You just use the data loader class and you pass in the data sets that you have created, this MNIST. So I should have probably called this MNIST data set just to differentiate. Okay. So let me run that. It's not going to download it a second time because it has already downloaded it. That's also the beauty of this. It first of all checks if it has already downloaded it. And if it is, it doesn't bother downloading again because the data set doesn't change. So we'll pass in the MNIST data set, okay? And the other parameters you can pass in into a data loader like we did with sklearn is the data, the batch size. So remember, the essence of a data loader is to take your data set and split it into smaller batches. So that when you are training your model, you are not going to load the whole thing. That's what we call the stochastic gradient descent. Remember, when we say stochastic gradient descent is training on mini batches, smaller batches of the thing. Okay. So we can specify a batch size, let's say maybe 32 or 64. So let me just go with 64, right? You can also decide to shuffle. There are other things, shuffle. If you are training a model, you typically like to shuffle, right? But if you are doing evaluation like testing, you may not want to shuffle. But in this case, since we just want to look at how the data set looks like, we have not yet started training. I'm not going to shuffle it. So now I have a data loader. So with a data loader, it's now easy for you to get um, one batch, right? To get one batch, you simply access it the same way you would have accessed a single row, right? And okay, so I think I did the wrong. This should be um, it's a generator actually, so I cannot. I'll have to convert it to a list, right? So let's convert it to a list, and then I can get the first piece of it. Okay. All right. So yeah, so this is this is an interesting thing because our data loader, okay, let me just do this instead of trying to get, I was trying to get trying to convert it to a list. Our data loader is actually loading peel images. And it seems like um our data loader is not able to do much with it. Now, there's a way you can loop it for item in MNIST data loader. We can also print it. I just want to show you how we can do this. So again, uh, because this is touch, it is not able to work on it because the original data set is made up of peel images, as you can see. And PyTorch doesn't know how to deal with peel images. So what we do now is we will pass in a transform, right? In sklearn, we call it pipeline, right? The pipeline is kind of something that you set up to kind of pre-process the data before it gets into the training, into the data loader. So that's the essence of this transform, which I had said initially that we don't need it. So let's add that. Let's add that. So we're going to add a transform, but we need to create transform first. So what's the transform that you are going to create? What's the nature of a transform? You first of all need to import to create transform. You first of all need to specify what transformation do you want to do. Transformations, you can specify them um, as the transform class has some specific transformations you can do. So let the transform package rather. So touch has that touch. has the transforms, touch vision has the transforms. So the transforms, maybe I could have added it here as well, but it's okay. The transforms allow you to transform more images, right? Um, they give some, standard transformations that you would normally do to images, because touch vision is a package that is just a utility package for image task, right? That's why it's called touch vision. So that's why the data sets has all kinds of data sets for image, training and all of that. So it also has a transforms which contains pre-canned transformations you can do to the different images before it goes into the pipeline. So let's create, um, you can stack transforms the same way we stacked, transforms in sklearn. We can also stack transforms here. So you can say mnist transform, right? We use transform dot compose. There's a function called compose that allows you to combine multiple transforms. Okay. So you just specify the transform that you want to do. To tensor is the one we need for now, because the to tensor allows basically will convert, like you can see here, it converts the PIL image to an ND array. Oh, sorry, a PIL image or NDR to a tensor, that's a touch tensor, right? And can even scale the values accordingly. Even though I didn't want to scale because I wanted everyone to see the actual values. But remember, all this while we have been dealing with integer values, numbers in the range of 0 to 255. But because those numbers are too high, remember, if you're training a neural network, or even any model for that matter, those numbers are pretty high. So you have to do standard scalar and all of that we're doing, right? So the transforms would do that. Even though there is a normalization that we'll do as well, which we'll talk about when you are training your model. So I've now created this. So I can now specify the transforms. Transform rather is mnist transform. Let me call this MNIST transform because it's still a single transform, even though it is a composition of multiple transforms. Now, so I now create a data loader, and I specify the okay, maybe I didn't type this. Oh, sorry. Yeah, this is in the wrong place. This should actually be in the data set. It is really at the point of it's really at the point of creating the data set that you should do the transform, right? It's at the point of downloading, so it will apply it in bulk to all of the data. So the entire data set, not to, yeah, that makes sense because you cannot be transferring one batch at a time. That doesn't make sense. That's inefficient. So you are applying the transform to the entire data set. So with that, you would be able to get your data loader. And we can now try what I was trying before to actually look at what is inside the data loader. Sorry, list. I'll convert it to a list just to look at what is inside the data loader. And maybe we'll look at the first array there. So you will see it's a batch of 64, right? Um, I can see what we get. So we now get the numbers as floating point numbers. A lot of them are zeros, which is interesting. The other interesting thing is that it also separates the Y values out, right? The Y value, which is the labels. So this is one good thing that the data set does. It separates the X and the Y values. So these are the X values. You could do the shape. Um, let me see if I can just get the shape directly. It probably doesn't work, but yeah, it doesn't have because the data loader is actually a is actually it's a generator. So you can see its you know configuration like batch size and everything. Now, if I want to get the actual stuff, I can do this. So this should now work where I am now able to go through each batch. And you can see because it's a generator, it is printing, it's yielding and printing, so it's faster. It's printing each tensor. So that's that. But if you look at this, you see this entire value, um, it's a three-dimensional value. So let's just look at instead of we are still doing exploration here, to understand how the value, how the data looks like. Okay. So how the data looks like, instead of printing the whole item, let me print item.shape. Item is not a touch tensor because that transform with it. Sorry, in touch it is not shape, it is size. Um, oh, uh, it's a list. Okay. Um, length. All right. So it has two elements to it, the X and the Y. I forgot about that. So what you have is you could actually split this and say X and Y, right? That's what you actually have. It's the X and the Y. So we can print the X dot shape and then the Y dot shape. Okay. So you see that they're all the same shape, basically. Um, we took a batch size that contains 32 images, right? And you can see the shape of the first one is 64, 128, 28, right? Um, the 64 refers to the batch, so there are 64, okay? There are 64 because this is one batch. Remember, each time we are doing this, we are essentially going through all the batches. So the total number of elements in a data loader, you can actually get the size. You can get it from data loader dot size. That's the total number. Um, so let's try that mnist data loader. Um, well, not batch size, but the entire. I think you would have to do the. You can retrieve the data set, but you would have to get the dot data dot size um mnist, okay, dot data length. So there are 60,000, right? You get the data set, you get the data value from data set. The data set is the underlying data set in the data loader, right? So the data, there are 60,000 rows. So if you're using a batch size of 64, we're going to get about 1,000. If we're using a batch size of 60, we would have gotten exactly 1,000 batches. So that means this thing is running 1,000 times, okay? So one single epoch, if we were training this way, one single epoch would be made of 1,000 cycles. Okay. So now I still want to delve in, right? So if you look at it, each batch, this is a single batch, right? It is what I just printed out here was the shape of the X value and the shape of the Y. The Y is 64. So that's just telling you that there are 64 um, samples in that 64 samples, 64 Y data, right? But on the X, you have 1 and 28 and 28. So this one is telling you the um, the third dimension. It has reversed the dimension here, by the way. Um, we now have what we call NCHW. That is the format. So let me talk about that a little bit when it comes to image. There is what they call, or general neural network training. There is the alignment of the dimensions. You need to know um what are these four dimensions, right? In images, it's difficult. So you need to know whether I'm using NCHW, right? Which is one convention that is normally used, okay? Or whether it is the second convention is NHWC, okay? So let me explain what this means. N means the batches or batch size, right? That's why in this case, the first number here is N. So the batch size is 64. Or if you were training on the entire data set, that would be the total number of, it's actually not the batches. So batches is the number of batches. So let's say N is the batch size that you are training in that time. But sometimes they use the terminology batches, right? And sometimes they even use the symbol B for it, which means batches. But that's what N means. C means the number of channels, number of channels. So what do we mean by channels here? That is the number, the amount of data, or the amount of, I don't know, a good definition is best, by using an example, right? Um, so if you have a single grayscale image that has only one value for the color, which is either it is white, which is 255, or it is black, which is 0, or somewhere in between that is gray color, right? But it has a single value, a single color, a single black and white color, or a single grayscale. That is one channel, right? So that means black and white or grayscale has one channel only. But if it is a full colored image, it has RGB. In other words, you need three values to characterize the color. You need the red component, you need the green component, and you need the blue component. So those three form three channels, right? So that's what channels means. Channel basically means the amount of data to characterize. It's a separate dimension, okay? Then, so that's this one here. So in this particular one, this one means there's only one channel. That is, it is a grayscale image. Then that's C. Then H means the height of the image or whatever it is, right? Sometimes it's not always images that we use, but in the context of image, you can say, okay, it is the height of the image. And then the fourth dimension is W, which is the width of the image. So you can see that in this, we did not clump everything down together into a single array because that makes it difficult to manage. It makes it difficult to manipulate and all of that. So rather, in machine learning, we take images and we maintain all the dimensions so that you can keep track of the dimensions in your head when you're doing stuff, no matter what it is that you are doing. Okay, so that's why you now have this. So the two formats that we have are NCHW, where you put the number of the batch size first, then the channels, then the height and width, or NHWC, which is the number first, then the height and width second, and third, then the number of channels last in terms of the ordering of the dimensions. Now, the ordering of the dimensions play later to how the numbers, the digits are done. By the way, if you want to switch this in the middle of a training, you use transpose. That's what transpose basically does. Transpose switches the order of the dimensions. So we can talk about some of those things later on. Now, so we now have a batch size. So if I take just one, right, I can now take this data loader again, right? I can convert it to a list, even though this is not a very it's not very efficient because um right, this is converting it to a list. It's going to print out the whole list. So it's going to essentially pull the entire data set into memory. This is not very efficient. That's why it's taking time. It's pulling this entire 6,000. The essence of data loader is to load only when you need it. The data loader is a generator. It does not try to load everything at once. It loads on demand. But once you convert it to a list will want to pull everything, right? So but let's go ahead. So I take 0. 0 is just the first batch. Okay. So again, still going to do this thing each time. So I think the best thing is to just get the first one, right? And then um okay. But anyway, um a better way to do it, yes, is to use next. Next is a function in Python that allows you to pick just the next item instead of trying to load everything. So next, but next only works on an iterator. So we have to convert the data loader to an iterator, which is what it does. So if you just do this, right, you get just one. And it is still made up of the two components. So this is one batch, right? Next gives you one batch, and that one batch is made up of the X values. It's an array that contains two values, the X values and the Y values for that one batch. Okay. And remember the shapes. So I could actually then decompose this and say X comma Y for just one, right? Same thing as I did before. I did that here already. So you can also decompose it here when you're looping through. Here you are looping through all of them, but here we are just picking only one. Okay. So you can now look at X dot shape. It's still going to have that same shape, right? There are 64 in this one batch. Okay. Now let's take one of the 64. So X0 is going to take one item in the batch. Okay. If we take X0 dot shape, remember we're now in NumPy land, so we can play around with it anyhow. So X0 dot shape gives you the shape of one single image. I can now use that in ImShow to plot. Okay. I can now use that in ImShow X0, right? Remember, it's not the shape I'm plotting, it's the whole this. Oh, ImShow needs to be plt.imshow. So with this is how you can then plot a single image, even though yeah, invalid shape. Right. So now why we have this problem is what I just mentioned. Okay. ImShow plots HWC. So this is a problem, and I forgot about this. ImShow plots HWC, right? While what we have here is what? CHW. If you look at it carefully, because we have taken just a single image from the batch. This image has a shape of, or rather, this NumPy array has a shape of 64, 1, 2, 8, 28, 28. So this 64 mm, means that it has 64 um, images, right? 64 samples in this batch. Okay. That's what 64 means. Then the one is the channel, the grayscale channel, right? The number of channels, grayscale. And then the height and the width is 28, 28. Because touch is designed to work with NCHW. Touch is designed to work with HW at the last dimension, the fastest dimension. The fastest dimensions are always the last. In other words, the number that changes um, first. That may not be something you can understand now, but I'll explain when the time comes. I'll explain that. So this NCHW, right, is the touch format, while NHWC is the in show format. As a matter of fact, in show, the format is actually CHW. In other words, sorry, is in show is HWC. Height and width first before the channel. That's why this is now failing and it's telling you that the shape is invalid. It's expecting 28, 28, 1. So how do we now do that? We use transpose. That's where I was saying you can now use transpose. Transpose is dot t with numpy, right? Or you could just do, let me see if transpose works this way. If it doesn't work this way, then we'll use np.transpose. So transpose, oh yeah, I forgot that. So when you're transposing, you need to specify the dimensions that are transposed. Now, what is transpose? Transpose is, I guess I'll I'll end up getting into a little bit of that. But transpose is if you had physically, right? If you had a matrix like this, and the matrix had values 1, 2, 3, right? 4, 5, 6. Okay, so you have a 2 by 3 matrix. This is a 2 by 3 matrix. In other words, it has 2 rows and it has 3 columns. This is a 2 by 3 matrix. If you transpose this 2 by 3 matrix, it now becomes a 3 by 2 matrix. It now has 3 rows. So each of the columns will now become rows, and each of the rows will become columns. So you now have a 3 by 2 matrix. That's a transpose, right? And when you transpose it, this first row becomes the first column. 1, 2, 3. Okay. The second row becomes the second column. 4, 5, 6. Okay. And so on and so forth. So this is now 3 by 2. Now, if you're representing this as a shape in NumPy, the shape of this first column, the shape would be 2 because there are 2 rows, comma 3, right? That maps directly to what we just did now when we say shape or size in touch. The shape of this second one is 3 first, comma 2. So if you look at this carefully, transpose basically as an operation in touch or any of these tools is basically swapping this, right? Swapping 2 dimensions. That's what transpose is. So that's what I want you to see that as a general understanding for transpose. This one, we can easily visualize it because we're actually flipping 2 dimensions. We are flipping the 2 dimensions here are the, the height or the batch or the number of rows, right? We are switching it with the height or the column, number of columns. So we change a 2 by 3 matrix to a 3 by 2 matrix. And we flip around the contents. That's transpose. So if I wanted to write this as code, I would do something like np, right, dot transpose, right? And then when I'm specifying the transpose, I need to specify which dimensions I am transposing. And the 2 dimensions I'm transposing are dimensions 2 and 3. In other words, I am exchanging those 2 dimensions. I'm switching their places. That is transpose. So I needed to clarify this before I now explain how we will, because the next question now is how do we move from a CHW to a HWC? We have to transpose and we have to do 2 transposes. We have to transpose 2 times. The first transpose will transpose this 2. The second transpose, when we transpose this 2, we now have 28, 1, 28. Right? Then the second transpose will transpose this 2. We now have 28, 28, 1. You need to do 2 transposes, right? You need to specify the 2 dimensions that you'll be transposing. That is the key thing. Okay. So let's go ahead and do that. So we have CHW, so we need to transpose, right? So we need to transpose the CHW to HWC. And that will take 2 transposes. Yeah, so it gives you transpose 1, 2, 0, but that's not really correct. It's just a single transpose. We are going to transpose multiple, not a single. So we'll first of all transpose transpose the entire array, right? So we can say x equals x dot transpose, and we're going to specify the dimension. So it's good to check what should come here. We'll transpose 1 and 2, dimension 1 and 2. That is this one will transpose, will exchange their positions. That will now give us 28, 1, 28. That's the first transpose. Then we'll do the second transpose again. And we'll now do 2 and 3. Sorry, one and two. Yes, two and three. So we're now transposing this. So it now becomes 28, 28, 1. Then when we finish, we can then check the shape again, x dot shape, and see what we get. So you can see we have changed this. By the way, because we transpose dimension one and two, dimension two and three, we did not transpose dimension zero, which is the batch dimension. The batch dimension remains. We only change the this. So that is why I can put the n in bracket, right? The n is still there because I'm trying to essentially transpose everything. Okay. Um, so these are some of the pre-processing that you would do with images, right? Now, I should not run transpose again because if I transpose again, I'll end up transposing 28 all the way down here. So I now have x dot shape as this. So I can now plot this. I don't need to transpose it in here. The value now has been transposed. So the first one now has the right shape. Okay. And you can see it as plotted. And if you look at this, this is what I don't know what letter is this. You can plot any number of x's. That's one. So one batch contains one sample, which is one squiggly, you know, image of a handwriting. This is X1, this is zero. Okay, and so on. This is three, data three. So this is Ebony's data set. We are now essentially looking at them one by one. You can run. Remember this particular X was a single batch I took that has 64. So I could decide to just uh, plot each of them. So I could do something like for I in uh, range of 64. Well, we can just go with that. And then we do a subplot. It's good to do a subplot. The subplot allows us to basically plot many of them at a time. So we do a subplot, and the number of the third dimensional subplot means 8 by 8, right? Since 8 rows by 8 columns, right? Is the third dimension. Then the number of images. Okay. No ticks, no X and Y ticks, because X and Y ticks is what is giving all this stuff. So no X and Y ticks. Then grid is false, so that doesn't draw it. Then you do that, and we can now do lots of intro XI. So the XI, that particular X. And that's it. So if we run this, we are now going to have those 64 images. And because we made a 8 by 8 grid, right? It's 8 by 8 grid. That's why 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 8. So that's why 64 is a good number to use. And 8 by 8, you get 8 times 8 is 64. And this is it. Right? So you have kind of plotted the numbers that MNIST. So this is how MNIST looks. This is how the MNIST data set looks. Okay, so now having done this intro, which I hope will really help us to understand um, when you are doing this training, right, and how to manipulate images, we will now go and look at the actual training. So in the training, um, we are going to train a simple convolutional neural network. To train a simple convolutional neural network, right? We use MNIST. MNIST has 70,000 images. 60,000 of them are for train and 10,000 of them are for test, right? That is the train test click ratio. That's why if you look at this one that we loaded, and you remember we saw 60,000 of them here. Yeah, 60,000 of them because we only loaded the train data set. We only loaded the train data set. So where's the train data set? Or where's the loader? If you look at where I did the loader, uh, yeah, so this is it. So you can see that I only loaded the train data set. So 60,000. Then the test is 10,000. So it's a total of 70,000 images of handwritten digits. And we have printed out a batch of it here. So you can see we printed out a batch that is made up of 64 because we use our data loader, and data loader will specify batch size of 64. So it loads the first batch. We use next here to just load only one batch first that is made of 64. And then we went on to do the experiment that we did, and we found out that for you to be able to display, you need to actually do two-step transpose because while touch loader is going to load it as NHWC, right? We have NCW, NCHW. The other thing, which is why these images, I didn't mention that, which is why these images look funny like this, because you may be asking, this is a grayscale image. Why is it having yellow and violet? It's because touch uh, the touch to tensor actually did normalization. If you look at it here, right, it did normalization, right? It says converts a PIL image or NDRA to tensor and scale the values accordingly. It scaled the values to a float tensor, right? It scaled the value to a float tensor. So us now using that float tensor to print did not give us the original image back. It did not give us the original image. As a matter of fact, if we were to take the original data set and just pick only one single element and print, let's try that. If you take the original data set, this data set, and take the data from it, right? Let me just inspect it. First one. You can see, let me see the shape, right? So the shape you can see is 28 by 28. So each of the data is a single image. Now, if I were to use this same printing image printing this thing for each data, each of the elements in the data set, rather than using XI, right? We'll just take maybe the first 64 images, right? First 64 images. So we are now going to use the original data set data and print without normalization. Oh, there's still normalization. Yes, there's still normalization because I passed in the transform as part of the download of the data set. So what I will do now is I'll get a new data set without normalization. I'm not going to do that tensor. I'm not going to add that tensor transform, right? I'm just going to um, I'm going to copy this and I'm going to download this because the MNIST is still the whole data set is normalized. So let's say I unnormalize, it's unnormalized, is raw. Let me just call it raw, right? So I'm going to remove the transform. So I'm going to get the same data set, right? But without applying a transform. That's the beauty of transform. It's not going to re-download it because the data set is already there. But now I have a version of data set that is not um, normalized to tensor. So what we now have is the raw PIL images, right? Raw NNIST data set dot data, right? Dot I. So we're going to get the first 64 again. And we're still going to print it the same way we printed the 64. And let's compare the difference. This time around, we did not do anything. Well, okay, it's still the same, I guess. So I was going to say that I actually expect this to be black and white. So there is something, here. We need to normalize it. It's showing colors when it should actually be, um, black and white. But anyway, um, we're going to talk about normalization as we go on here. So anyway, that's the MNIST data set, right? We start with that. We import all of our stuff. So remember, we need the touch.nn so that we can build a neural network. What is the CNN, the convolutional neural network? We are going to use a LeNet. Remember, a LeNet is just two convolution layers, right? A convolution layer, a max pooling layer, right? And then another convolution layer, and then we now have the final fully connected layer. If you remember where we talked about LeNet, let me just show you the LeNet. So we use LeNet for this, the first neural network architecture or convolutional neural network architecture that was used. Let me just show you what it looks like. Um, Oh yeah, so it was actually very simply here. You have a convolutional layer, then you have a pooling layer, which you can either use max pooling or average pooling. Then you have another conv layer, convolutional layer. Then you have another pooling layer, and then you have a fully connected um, single layer or maybe two layers of fully connected. So you see how you can do that now. So with Lynette, um, yeah, we need to bring in the touch.nn so that we can um, do um, let me see. I want to make sure I'm opening the right one. So let's see. Yeah, but I believe it was the right one, but I just want to be sure. So because we run out of time, we'll do transfer learning when we come in next week. But I think we had already agreed that we'll slow down a little bit so that everybody understands what is going on. So I hope this is okay by everyone. You can give me a thumbs up if you're okay with taking the time to go through this. So yeah, so we have all of the imports. We need the NN so that we'll do the architecture, right? Then we have the optim, which is the optimizer, right? That's where we'll get the optimizer, whether it's Adam we want to use or whatever. And we have the data loader where we had already done this bit of hands-on here with basic image manipulation, where we can load the data. Then we need the data set, right? Which is what we use to load the touch vision data set, the MNIST, and then the transform that we use to do the to tensor so that PyTorch can handle that data set. Otherwise, it's going to be dealing with a PIL image, which it was fighting against that one when I did that, and we all saw it. Then matplotlib for plotting the images so that you can actually see the images as. Then one other interesting thing here is because we are now training really deep neural networks, it's good for you to check out if you can use a GPU. So this time around, I'm actually going to show us how to do that. You can go to this connect button here, right? And you can choose um, connect to Google Cloud Runtime or change runtime type. So you click on change runtime type and you can see that we have a T4 GPU. If you're on the free tier of Google Colab, this is the only one you will have. And then this one is a TPU, but a TPU typically will still not speed things up because PyTorch doesn't know how to use a TPU. It will still fall back to the CPU and it may not be fast. I've not really tried it, so I don't know, right? There are other ones here you can see that are grayed out because when you subscribe to Collab Pro, which is a paid tier, then these ones will become available to you, right? And then there's also Collab Pro Plus, which is a paid tier that is a bit higher that you pay and you get more of this stuff. But for now, yeah, you can just use a T4 GPU, which is the slowest of all of these GPUs, but it's still faster, much faster than using a CPU. Okay. So click on save. Now, so we'll start again because the runtime is going to switch. It's showing you here that you're now on a T4 GPU. You can click again just to confirm T4, right? So you're on a T4 GPU. So we'll start again. So I'm going to run this to import all the dependencies. Then, like I said, here you can now check. So before, when I was not using a GPU, it was the device was a CPU. But now that I've switched to a GPU, if I run this or when I run this now, you'll see it will have switched to a GPU. So it's going to show you CUDA, right? CUDA is NVIDIA GPU, right? Powered by NVIDIA software. The CUDA is NVIDIA software that helps you to essentially translate the Python code that we are writing into the code that the GPU knows how to run. The GPU does not run on Python. It doesn't run on C or C++. It has a special language, and that language is CUDA, even though CUDA is based on C language anyway. So so that's just a name they give to it. So that's CUDA. So we use Lenet. So like I said, you can see Lenet is just a conf layer, a pooling layer, another conf layer, a pooling layer. So it's a two layer basically. The pooling layer is not really a layer per se because even though it does something, right? Remember what a pooling layer does is it reduces the feature, the output feature size, right? So it reduces it so that it becomes easier. It becomes easier eventually when you want to convert it or flatten it out. So linear is very simple. So you can see the whole thing here. There are two ways you could do this. Remember, I say you could either do it this way or you could use a sequential. But let's do it this way, that just to show as an example. Now let's see if we can understand some of these things. Okay, let me put this as NN sequential first so that it's easier to understand. Maybe when the amount of code is less, right? There are two ways you could do this, right? The first one is using NN dot sequential. NN dot sequential is just a way of stacking layers quickly, easily. So you could say Lenet, right? Lenet, right? Lenet network. Lenet net, Lenet net. Okay. So net NN dot sequential. Okay. Then this sequential, you can specify each of the layers here. So let's start off, right? The first layer you are going to use, remember the first layer is a convolutional layer. Okay. The first layer is a convolutional layer. So this convolutional layer, remember this is what? HWC, right? Height, width, and channel. So there's one channel, right? This one channel is again the black and white. So it's HWC. Interestingly enough, our PyTorch, remember our PyTorch loader is loading and converting it to CHW. So pay attention to that. We'll have to deal with that problem. But yeah, so let's assume it's HWC. So how you get a convolutional layer in PyTorch is to use the conv2d function, this conv2d class, right? You specify it that I want a convolutional layer, a single convolutional layer. You specify the number of inputs, which is the input feature size, right? And then the number of output, which is the output feature size, number of input features, number of output features. Okay. Oh, sorry, not the number of input features and number of output features, but rather the number of input channels and the number of output channels. That's, you can see it here clearly. The number of input channels and the number of output channels. Of course, the number of input channels is one, which is just the color channel. There's only one color, right? With convolutional neural networks, we don't deal with the feature size. You don't specify it in the when you are creating the thing, right? Unlike with fully connected layers where you specify the number of inputs, right? You don't specify the number of inputs in conv2d because conv2d can actually calculate all of that. But what you need to specify are the number of channels, right, that are going in and the number of channels that are going out. So the interesting thing is that you can actually look at this thing and you can see that what's happening is the Lenet was one input and six output. Now, the six output, these are things you can choose arbitrarily. So this means this six output basically means six filters. Remember, each filter will essentially, um, each filter will map to a new output channel. If you remember that animation that we saw, which I can show again, each filter maps to a new output channel, right? That's how you should look at it. This is a whole filter. It operates on the entire image, right? If there's max pooling or padding is zero or something, it will reduce the size of the feature map, right? The output, the size of the output. Okay, it's going to reduce that, but each of these filter will generate a single feature map, single output, feature map. And yeah, let me just share that animation again so we can, Um, yeah, so you can look at that and you see how um yeah. So if you look at this, right, this is the animation that helps us to understand how these things map. So this is a single filter. It scans through all of this. It's scanning all the dimensions. It is the front face here. You have each of these kernels in the filter that are basically going through, right? And then all of the kernels are summed together, right? And it gives a single output layer. So the next, a single, essentially a single channel, right? What I'm now calling not an output layer, a single output. Yeah, okay. A single output channel. That's the correct terminology. So the next filter, this brown filter, gives another output channel to the brown output channel. These two green ones are slightly different colors, shades of green. Also give you two new output channels. Okay. Then another filter here, this one cyan, gives you another output filter here. Sorry, output channel. Then you have this blue, and then you have this violet, and you have this pink. Each of them also gives you an output. So you can see that the number of output channels you get, which is this dimension, is corresponding to the number of filters. Each filter generates a new output channel. And if we want to look at it um, using that dimension, this is now the channel dimension, right? So in case it wasn't very clear, this is now C, the channel dimension. Then the other two dimensions are the H and the W, that is the height and the width. So you can look at this as the height dimension, and you can look at this as the width dimension. So you end up having height and width as additional dimensions. So this is height, okay, and then this is width. So effectively, you have transformed, if you look at this also has height and width, right? But the height here is more, and the width here is more, right? And the channels here are more, right? So you actually have uh, this dimension and they're related. This is the width. So you can call it WI for the input width. And this is the input height, which you can call it HI, right? And then this is the input channels, the number of input channels is CI. While here you can have this as the output width and the output height, right? And the number of output channels. So now let's look at the maths of this. The height and width of the output depend directly on the size of your filter, right? The height and width of your filter or the kernel, this kernel size, whether it's 3 by 3 or 5 by 5, depends on that. Depends on the stride. In other words, how many steps it jumps as it is scanning like that. And then it also depends on the padding that you put around the image, the feature map of the incoming image. Okay. So those three determine the size of it. So those three can easily be calculated by PyTorch. So PyTorch doesn't need you to tell um, it the image dimensions, the HI and the WI, because those ones it can calculate from those parameters I mentioned, which are hyperparameters, the kernel size, the stride, right, and the padding. Those are three primary things that you can use to calculate what the output size or height and weight will be with respect to the input height and width, the ratio, basically. But what you can, and then you also, each kernel, the depth of the kernel is going to match the depth, the number of channels, because each sorry, the depth of the filter is going to match the number of channels because each filter is made up of kernels, right, that are stacked, right? And these kernels that are stacked, in other words, this depth has to match so that each kernel will only address um, a single channel on the input. See, these things are moving around, so I cannot really, but this, you see this depth, each kernel's channel, the number of channels in the kernel or in the filter, the number of channels in the filter must match the input channels because the filter is basically a stack of kernels, right? Where each kernel is designed or learns features based on one channel, single channel. Each kernel is one single channel. So if you have 10 channels, then the filter also have 10 channels. You have 10 channels basically start to form a 10 channel filter. That one single 10 channel filter, everything will be added up. When all of this convolution is done for a particular tube like this, it's going to be mapped to a single point in the output. So think of it as a new pixel in the output. But in the output of that, we don't really call it pixels anymore. But it will not be recognizable as a pixel anymore. But it's just features. So I hope this kind of gives you an idea of how the maths of convolution is done. Okay, so now when you are now creating your um, conv2D layer, that's why you have to specify the number of channels coming in. And in this case, because it is a monochrome image, right? A grayscale image, there's only one channel. So that's why the input is one channel. That means that the filter will have only one kernel, right? You can see here, we specify the kernel size, but we don't specify the filter depth, right? Because the filter depth should match the input channel size. Since each kernel in the filter is supposed to deal with just a single channel in the input. So the kernel size is 3. And even when you're specifying kernel size, kernels are always assumed to be square. So if you specify a kernel size of 3, that means it's a 3 by 3 kernel, like what we saw in this animation. This animation is we are using 3 by 3 kernels. So 1, 2, 3 width and 1, 2, 3 height. Okay. Then the padding is 1. So remember we talked about padding. Padding is what you add around the fake pixels that you add around an image, right? So a padding of 1 means you add one layer of or one row, one column, of fake pixels, zero valued pixels around the input or each input, basically. And like I said, padding sometimes helps for you to maintain same width going across. And you need to think about the padding maths of it. Now, um, if you look at this one, it has padding of 1. It has kernel size of 3. We didn't specify stride, by the way, in conv2D, right? This if you don't specify the stride, the default stride is 1, as you can see. If I hover over this and all the parameters, you see kernel size, right? That stride, the default stride has a value of 1. You can see it here. And then you have a padding. So padding, you specify the padding, and then you can also specify the size. So the size of the padding, which is in this case 0. 0 means no padding. Okay. Then there are other things like dilation and so on, which I'll talk about later. So these are the hyperparameters that you will pass into each layer. Okay, so this is the first layer, the first conv layer, right? It's going to take the single channel and it's going to give us 6 feature channels. So effectively, what this means is that we are going to have a filter. Each filter is going to be of depth 1, basically a single kernel. But we're going to have 6 filters because each output channel is created by a separate filter. Okay. So that is the first of 2D. Then after that, we will now have a pooling layer. So the pooling layer here is a max pooling layer, as you can see, right? By the way, I have to put a comma here because we're using sequential. So each of this is basically um, a new um, argument to this sequential function. And the reason why it has red is I've not finished what we're going through it. So you have to have a comma at the end. So after the conv2D, you now have a pooling layer. And the pooling layer we're using is max pool. Well, let's think about this first. Why do we end up from 28 by 28 by 1 to 28 by 28 by 6? The 1 to 6 is easily understood because we have moved from a single channel to 6 channels. So that's why we now have 6 channels here. But why are we still at 28 by 28? Because if your kernel size is 3, right, and you have a 28 by 28, right, you are going to end up with a padding of 1. Actually, this is not, um, if you have a padding of 1, right, in a 3 by 3 kernel that is running through a 28 by 28. Um, let me validate this, right? Because I'm not feeling like it is correct, but let me validate it. So 28 by 28 means you have your feature map, right? The image itself, the flat image is 28 by 28, right? Um, so 28 rows by 28 columns. So you have 28 by 28. Okay. Then, but you are taking a kernel that is 3 by 3. So if you are taking a kernel that is 3 by 3, the number of strides you make would have been um, 28 minus because the stride is 1, right? It is always going to be 28 minus 3 plus 1, which is 26, right? We would have reduced the dimension of this thing to 26. Why? Because remember, you are putting a 3 by 3 kernel here. If you put a 3 by 3 kernel here, right, and you begin to move those 3 by 3 kernels right, you'll only be able to move 26 times before you get to this other edge. You'll not be able to do the 27 and the 28 because there is no more place to go to. So that's why the padding of 1 allows you. So if you have a padding of 1, that means you add extra fake pixels here. Then it means that your 3 by 3 kernel starts earlier by 1 and finishes later by 1. So it returns back the 2 that you lost because of the width, due to the width of this kernel. So that maps back to 28 by 28 output. Okay. Please go and try this out on your own so that you understand. So that's why we end up still getting 28 by 28, right? So whenever you have a kernel size of something, the padding, because when you put a padding of 1, this padding of 1 does not mean 1 at the end. It means 1 at the beginning, 1 at the end, 1 at the top, and 1 at the bottom. So it's actually 2 additional columns are added. So the number of the outputs would always be the original in. This is the formula. I can just give you this formula, right? The feature space, right? The feature width of the output, right? Remember when we say feature width, that is the output size, basically. The feature space, the feature map, the output, right? The feature space of the output, okay, is basically can be calculated. Let me just yeah, okay. Let me write it. I wanted to type, but let me write it. So the feature width of the output, okay, is derived by there's a longer formula, right? But it is going to be the feature width of the input, right? Plus the 2 times the padding that you put, right? So if padding is 1, that means you're putting 1 on each side. So that means the padding increases the width to, let's say you have 28 as the feature width in the input, right? Let's say you had 28 as a feature width in the input. If you had 28, then the new width will be 28 plus and a padding of 1. That will be 28 plus 2 times 1. Of course, you have 1 on each side. So that's 30. Okay. So that's a new width, right? Then you will now subtract from this the kernel size, right? Kernel size. So a kernel size of 3 means that you have lost 2 of those 3 spaces for movement of the kernel. The kernel will not be able to shift 2. That's 3 minus 1. The first one is there, it can move, but um, because it's width, it has taken extra 2 spaces more than a normal 1 by 1 kernel. Because a 1 by 1 kernel will give you exactly, without padding, a 1 by 1 kernel will give you exactly the same output as the input. So you start from there. Now, a 2 by 2 kernel, the second row or column will deny you of being able to achieve the full width by that extra 1 row you've added or 1 column you added in the kernel. right? So a 2 by 2 kernel will be -1. A 3 by 3 kernel will be -2. So it's going to always be kernel size plus 1 or kernel size -1, but minus minus is plus, right? So that is it. Then the stride is how many times you jump. Okay. So if your stride is 1 divided by stride, if your stride is 1, that means you get there, um, you know, is 1 by 1. So it's going to be the same thing. But if your stride is 2, that means you have halved the feature space. So this is kind of a relationship between the feature width at the input and the feature width at the output. Same thing with the feature height, right? At the input and the feature height at the output is the same formula that you can use. So what that means is that in most cases, if you have a kernel size of 3, which is 3 by 3, like we have here, then that will be feature width -2. So you compensate it by adding a padding of 1, which will be 2 times padding. That's 2. So that's -2 plus 2, 0. So you are back to getting exactly the picture out. So that's very key. So now we talk about the um, max pool layer. So the max pool layer, you can see the kernel size is 2. And the reason why kernel size is 2 is because you want to divide it by 2, right? The stride is 2, again, because you want to divide it by 2. So it's going to jump every 2 steps. Essentially, what a max pool with a kernel size of 2 and a stride of 2 does is something like this. Basically, if you have this as your input, right? This is your input feature again, right? Let me just go with maybe simple 1, 2, 3, 4, 5, 6, right? And 6 by 6, right? Or whatever. Okay. Then what's going to happen is that okay, let me do this much better. Let me do this much better. So if you have this as your yeah, let's start off with a square. So you have this right as your input feature, and then you have a bunch of this, right? 1, 2, 3, 4, that's 4, 5, 6, right? 7, 8. So you have 8 rows and then any number of, sorry, 8 columns and any number of rows. Okay. So yeah. Now you now take this and you take your kernel and your kernel is 2 by 2. So remember this is pooling. So pooling we take a kernel that is 2 by 2, right? So let's assume this is our kernel. It's 2 by 2. So that means we are taking a kernel of this dimension. We're taking a kernel of this dimension. Okay. So each kernel goes through this way. Then you have a stride of 2. That means that the next, it scans these 4 cells, right, in the feature, input feature space, and then it does max pooling. So if there are 4 values in here, it will take the maximum value. Of course, there will be 4 values because it's 2 by 2. So whatever are the 4 values in this um, you're going to take the maximum value of this. And that's what it will map to the output, the new output feature space. Okay. So in this case, for example, it will take um, 5, which is the maximum value. That's max pooling. Average pooling will calculate the average of these 4 values. Then it will now do a stride of 2. So stride of 2 means that instead of moving by 1, a stride of 1 would have been to move, if you didn't specify a stride, it would have moved here, not on this row, but on this row, it would have moved here. Okay. But that will overlap and it will not give us the benefit of pooling, which is we want to reduce the size of the output. So that's why you do a stride of 2. So a stride of 2 is going to jump on 2 and start here. So this a stride of 1 would move it 1 by 1, right? A stride of 1 would move it from this to this, right? The beginning of this from this to this. But a stride of 2 will move it from this to this point. So a stride of 2 keeps moving it that way, right? This way, and it keeps taking the maximum value. So you can already see that a stride of 2 will reduce the number of outputs to half of the number of inputs. The number of outputs was 1, 2, 3, 4, 5, 6, 7, 8, right? But the number of that's the number of inputs. The number of outputs now goes down to the max of this. So this will be 1, 2, 3, 4. So you're now going to end up with 4 um, outputs, right? 1, 2, 3, 4, right? That's for the first row. Then, of course, the second row is again a stride of 2. So the stride also applies both vertically and horizontally. So it's going to move horizontally and it's also still going to do just 4, right? And so on and so forth. So it continues like that. So you're going to end up with an output feature map that is going to be made up of, you know, is going to basically, reduce this dimension. So you can see it reduces the dimension half of what was there before. That's what max pooling does, or pooling generally, whether it's max or average pooling. The only difference between max and average pooling is how the next value is calculated. Max uses the maximum and average uses the average. So that is the max pool, right? So remember the layer 1 gets a 28 by 20 by 6. Then you do the max pooling. So the max pooling now gives you a 14 by 14 by 6. Then you now pass this into the next convolution layer. And the same principle applies, right? And you can see it's basically the same thing. We are still doing 6 to 16 now from 6 input channel, which is what we had here. The channels don't change, by the way. Max pooling or pooling does not change the channel size. Pooling changes the feature map size or output feature size, right? It doesn't change the channels. What changes the channels is a convolution. So you can see that those are two orthogonal operations that you can then adjust anyhow you like when you are doing your design architecture of convolutional neural networks. That's why they are very powerful, because you can adjust the pace at which, or the rate at which your pooling is reducing, or your feature size is reducing, without independently of the rate at which your features are also increasing, or your channels are also increasing, right? So, and that's all. That's basically what this does. It just does that. So this now is a conv2D, the second conv layer here, according to the Linnet architecture. And yeah, so you have the second conv2D, 6 input features or input channels, 16 output channels, right? Again, same kernel size, same padding, so that you still have a direct 14 by 14 to 14 by 14. And then you do another max pool. Again, same hyperparameters here. Kernel size still 2 and stride is still 2. So that will reduce it to 7 by 7. So by the time you finish this now, you now end up with an output feature size that is made up of 14 by 14 by, sorry, 7 by 7, because this max pool is going to reduce it to 7 by 7, right? By halving the thing. So it's going to be 7 by 7 by 16. Remember, 16 is the 16 channels. So you can then flatten this, right? And you now create a linear layer. So that linear layer now has to have exactly, but when you flatten 7 by 7 by 16, all of this become the inputs into the linear layer. So the total size, number of inputs in the linear layer, which is a fully connected layer, the input feature is going to be everything here, which is 7 times 7 by 6 by 16, right? That number of inputs. And then you choose a smaller number of outputs. So you notice that we actually did two layer for the linear output, right? You have to remember the commas as well. We did 2, right? And the reason why we did 2 is because it is not a good idea to drastically reduce your number of neurons, just drastically going from this 16 by 7 by 7. You can do this maths, right? You can easily do this maths to see what the value is. You see that 16 by 7 is 784. So going straight from 784 to 10 categories. Remember, there are 10 categories, the final output. We want to predict whether it is 0, 1, 2, 3, 4, 5, 7, and 9. So reducing it that drastically would be a problem, right? You lose knowledge. So that's why we need to have at least 2 linear layers. The first layer will drop it to an intermediate number of, outputs 120, right? From the 784 that we have here, which is 7 times 7 times 16. And then we now have another one that will just take that 120 and give us the 10. So that's the thinking behind the Linux architecture. And generally, that's the thinking generally. So you see that, yeah, this is me doing it with sequential, but this is exactly the same thing done using a class method. You just would make each layer as a separate um, element in the function. And then when you want to run the forward, right, you actually need to do flatten. That's the benefit of using this approach, right? It will be very difficult for you to do um, this. You need to, maybe we'll add a flatten layer because I think we should have added a flatten. Yeah, we should have added a flatten here, right? So I don't know whether there's a flatten layer. Um, Yes, there's a flatten layer. If you don't specify this flatten layer, you will have a problem of the dimensions not matching, right? So you have to flatten after the max pool. You have to flatten before it goes into the linear layer. Okay, so that's that. Now you can see that flatten is also done here. What view does is to flatten. What does flatten mean? Like I said, if you look at the this animation, what you always come end up with is going to be a cuboid. It's a long cuboid. It is not a single vector. The linear layers take single vector. So you have to essentially flatten all these parameters into a single vector. That's what that means. So you take this three-dimensional shape and change it into a single one-dimensional shape. Of course, the batch dimension is still separate, but we don't normally talk about batch dimension because we know that that's the batch, right? So, um, you now have a same this thing. So the way this works is that when you now want to do inference, it will first of all take the input through the conv2d layer, then the max pool layer, then the second conv2d layer, then another max pool layer, and then flattens, then the linear layer, and then another linear layer. Now there's something I've missed. There should be some kind of activation function in between. Because if you look at this, yes, we did this, right? But you see that here, we do the conv1x, which is conv1x, right? Then we added a ReLU. We did a ReLU to it, okay? That is the x. Then we take that x and we pull it. We do the max, okay? Then after that, we take this x that comes out from the max pooling, we put it through the second convolutional layer, and then we ReLU it. There has to always be activation function. Otherwise, this whole thing will not work like we have seen before. And then we take this X and we max pull it again, right? And then we flatten it, right? Before we now put it into the fully connected layers. And we put it first into the fully connected one. And then the output from fully connected one goes into fully connected two. And then that is the return value. So the missing thing we have, we don't have ReLU. ReLU has to come immediately after the conv1, before the pooling layer, right? The activation has to come before the pooling. So I mean, we don't have it in our sequential. So it means that in this one, we have to add the ReLU, right? So we have to add nm.ReLU, okay? And we just need to do ReLU. There's nothing special. ReLU will be able to read the inputs and it will be able to read the outputs. Okay, we do this, and then here we also do the ReLU as well, right? And with that, we are complete, right? Conv2d ReLU, max pool. That's always how it is. Another conv2d ReLU, and then max pool. Then we flatten, and then we do two linear layers, linear one, linear two. So this actually works. Both of them are equivalent, essentially. These two will do the same thing, the Lenet and this other one. So let's go on to the training. So specify batch size, specify learning rate. We know we're using Adam optimizer, 10 epochs. So remember, there are 60,000 samples in the data set. We are taking batches, so it's likely going to give us around 1,000 batches. So you don't need too many epochs, right? And that's why we even have a GPU here so that things will be fast. Right. So remember I said you do transpose, you do transform compose. You need to do this to tensor because if you don't convert like we saw, if you don't convert the peel image, the MNIST gives you the original peel images. If you don't convert the peel image to PyTorch tensor, you are going to have problem. Now, like you've seen, it also does this other thing, right? It transposes the HWC to CHW. So that is what PyTorch needs for training. But you need to convert it back when you want to print it, right? When you want to print the image. Now, the other thing is that there's also a normalization that you do, standardization, right? You standardize using very specific values. That's one other thing. The reason why is if you want to do the same test, you now want to run tests, you need to normalize by exactly the same values. Otherwise, you have essentially changed the range, standard deviation, and all of that. The data distribution has changed. So it is actually a good idea to normalize, right? But normalize with the same values. And the MNIST data set, these are the two values you normally use for normalization, right? The mean, the mean values and the standard deviation, right? They are just single values, but you have to put them as a tuple like this. Okay. So you do that transform, then we download the training data set. Um, we download the training data set, and that training data set, um, we specify download it through, we apply a transform. We put in a data folder, which you will see here. Then, yeah, so it downloads everything. You see everything here, right? So we have the training one. Then the data loader, like we said, you specify the data load. Because we are training, you have to shuffle. Whenever you train a model, you have to shuffle. So always remember, it's passing the training data set to create a data loader. Specify the batch size. So we have already specified the batch size as 64 here, right? That's what we are using here. Then you shuffle, right? Always remember you have to shuffle. Then test data set, the same thing. So this time already specified train is false. That means you want the test data set. And you see apply same transform. It has to be the same transform. Even though technically, yeah, for MNIST, it has to be same transform. Otherwise, the data set will not, um, um, the two data sets will not be in the same kind of distribution. And that's wrong. Okay, so we now create a model. So there are two ways you could use this Lenet class, like what this one is using the Lenet class, or you could just use this Lenet that we use sequential. Any of them would work. Okay, because we have seen that they are both the same thing. Then remember to device. So you move it to CUDA device. You specify your criterion because we have multiple classes in the category using cross entropy loss, right? We're using Adam optimizer because we want to get it there fast. Learning rate for Adam optimizer is normally in the range of 0.001 or so. So you can see that we're using 0.001. Okay. Then yeah, you pass the parameters. So we now have our stuff set up. I now create a function for the training loop, right? This function for the training loop allows you to basically run multiple batches, okay? So you specify the model you want to train, the device you want to move it to, the training loader, so the data loader, okay, the optimizer, the criterion, and the number of epochs. So we set the model in training mode. We initialize these variables for this particular one, the training loss, the number of correct values. This is for calculating accuracy, but there are other ways you can also calculate the metrics that you use to measure and all of that. Total and correct is for calculating accuracy, basically. Then losses, you track the training loss. We could have also done the validation loss, but for now, I'm just showing you training loss. Eventually, in the task that you do, you actually have to add validation loss and calculate things like cross precision recall and all of those additional stuff. Okay, now, so you now run through each batch, right? So remember, you are using your data loader, the train loader, which is your data loader, to run through it batch by batch. So you go through each batch. Remember, each batch is giving you 64 because batch size is 64. So each batch is giving you 64 samples. Okay, so we are training on 4 samples. Now, we have seen this already that the shape of the data is batch size, right? 128, 28. So this is B CHW. Okay. And the shape is also just the batch size, which is the number of outputs that you want to compare with. So move the data into the same device. So the data, which is, again, when you are loading this, you actually will have the batch index, and then you have the values. These values are made up of the X and Y values, right? The X values is data, which I could have called X anyway. And the target is the Y values, which I could have called Y as well. So don't allow this to confuse you. Maybe I should call it X and Y just to help everyone understand, right? Data is X, right? and target is Y. So that was just a different nomenclature, but it's the same thing. Okay, so you move them to the device, X to device, Y to device. You do zero grad on the optimizer, meaning zero all my gradients, right? And because we're starting afresh, train, run prediction, run the model X values through the model, you get a prediction, and then the target values, which are the Y values. You now do criterion to compare. Normal thing we've always been doing. You get the loss. You run backward propagation, loss of backward. Then after backward propagation to calculate the gradients, you run optimizer.step, right? To apply those calculated gradients to all the parameters. And then you can now go ahead and aggregate values that you use to print later on. Training loss, you keep adding number, the loss values, you keep updating. Then um, to calculate a bit of accuracy, you find the predicted class that has the highest score. To do that, grade contains all your prediction, right? Um, and remember, because it is, I think I don't have time now to go through this, but Parade is actually going to give you a probability distribution on the output. It's not going to give you a single value to say, oh, this is the one that I predicted to be. No, it's going to give you probability based on the categories. So, for example, anyway, I'll show that at some point soon. But it's going to be like the probability that this thing I am seeing, this number that you scribbled, I'm seeing, the probability that it's a 0 is 5. Probability that it is a 1 is 6. Probability that it is a 9 is 50. 70. That's what it does. So you are actually going to take the one that has the highest probability, right? Max gives you two values, the actual value and the index of the actual value. What you actually want is the index of the value, right? Not the actual value. Again, I'll try and clarify this after the training is done. So this gets those values, right? The predicted is what we call argmax, right? Which of them actually has the highest probability? Okay, that is what you use to calculate accuracy. So anyone where the predicted value is equal to the target value, right? Um, those ones, this equality will give us values of 1 for those ones. And the ones that are not equal, the equality will give us values of 0. So you just we sum the number of ones. That tells you the number of accurate predictions. As simple as that. Then every 100 batches, we print stuff out. So typically, we don't print every batch because that will just make your stuff too many. Okay, and that's it. Okay. Then you can also calculate total average loss, matrix, accuracy, which is the total number that was predicted correctly, divided by the total number of samples in that batch or in the whole data set. Okay. Average loss is strain loss divided by the total number of data in the data set. Okay, so you return all of those values, and that's just a function. Then test function, the same thing, except that this time we use touch no grad, so we don't calculate any gradients, right? We put in evaluation mode, and we now use the evaluation data this time around, the evaluation, the test loader to load and calculate, um, you know, the metrics. So again, same approach, basically the same thing. Everything is almost the same. Okay. So we now go to the main training. So in the main training, you are now going to run each epoch, you're going to do a single training of the entire data set using the batches. So we specify the number of epochs. We're starting from 1. We could have started from 0, but 1 because we just want to easily track the number. So we can run this. This should run pretty quick on your GPU. Okay, so we have an issue where something is not on the GPU here. So I need to check what I forgot to move into the GPU. Let's see. Yeah, I think X Oh, okay, so this is a problem. The Y, I forgot to mention the Y should be moved to the device. So that's the problem. I think I knew I had missed something. Okay. Okay, so with that, so Y target is now Y. Target is now Y. Okay. Okay, so that because I just decided to change those things. Okay, so I'm not going to do that for the test device. Kind of still the same thing. All right, so they're now all on the same device, and you can see your training epochs is moving really fast because we're using a GPU. In a few, this is just epoch one. I think I specified 10 epochs. So you can already see the losses have dropped. Okay. So epoch one runs and we get to a loss of 0.07. 96% accuracy, right? It goes from 11 to 96% accuracy. Or sorry, 96% completion. But the loss is 0.07. And then the next epoch, right, on the same data set, right? Each batch again. So we get from 0.06 to 0.33. So it's actually learning, it's getting better. And then third epoch, right? Third epoch again, it goes from 0.028 to 0.088. So I don't know if this is an overfitting issue or something, but maybe some new data, right? Um, yeah, but I don't expect LNet to overfit, right? But it did look like it had gotten to a very low value of loss here, right? And then it started going up. So that's interesting. It's possible that maybe it has started overfitting. That's where you could do regularization, all of that. I didn't do any of those things here. I didn't do regularization. I didn't do early stopping or any of those things, right? I probably didn't need to do 10 epochs on this because it does look like it is um, kind of jumping around here. There's a lot of jumpiness here, right? But there could also be because it is batched data. Um, so yeah, but we'll get to 10 epochs and then we see the rest of it. So let me also cue this. So we now start visualizing. So all of the things that we talked about, we are going to plot epochs. We are going to plot we are going to plot you know, results and all of that. These ones are things we are already familiar with. Then we'll do the image visualizations. So I think I've showed you how to do that already. So in the visualization, you can okay here. First of all, I have I create where I can save the model. Later, I'm going to show everyone how you can save to your Google Drive so I don't lose your training progress. Because when you start training really big models, you find that you actually have to train for a long time. And sometimes days, sometimes weeks, or even months. If you are doing that and you don't save it in a more permanent location, you lose your progress. So you come back and start from scratch. That doesn't work. That's not how training works. Training works, you get to a certain point and then you come back and yeah, so you can see the plots. Training and test loss, I've been plotting them. So test loss starts pretty low because by the time you do test validation, evaluation, training has already gone down a bit. So you can see training goes, and then training accuracy also goes up and keeps going up, right? It goes up to about 99%. But test accuracy, you can see it's jumping up and down, jumping around. So if it starts going down seriously, then you know that it's beginning to overfit, like we talked about. So that's what to be careful about. Here you can even see at this point, well, it's just like averagely, it looks like it's flat. But if it starts going up here, then you may also begin to think that maybe you're overfitting. And that's why I was saying that we got to this point. I think at this point, we're okay on the fifth epoch, but we started overfitting afterwards, right? So at this point, we should have done early stopping. Any um, further training doesn't seem to have improved validation loss anyway, or testing loss. Okay, so visualizing the image, first thing we save it, right? It is now going to be saved in mdcnn.back, right? Touch knows how to save that. You see it here, it is saved in a touch format, so you can load it back. Training history, by the way, was also saved. The chat was also saved, right? You can see where it is saved. here where matplotlib actually does that save figure. So you can save that plot so that you can check it out later on. Then yeah, so to now visualize, right? We basically use that same code I showed you where you take the indices, but there has to be oh, I forgot to mention that image show, you could have used a CMap of gray. So that's why we're not getting the grayscale. Should I use a CMap of grayscale so that NumPy will represent them proper, right? That's how you get the grayscale image. Okay. Um, yeah. So the squeeze, I don't know how come they did not do the um we have the subplots, we have subplot title, and then we look through. What I see here is random indexes, the image and label, right? And it's the transpose that I have, you know, I don't see transpose here, but yeah. So this is the loop that will plot data set, and then this is the loop that will visualize data set, visualize predictions. Yeah. So I'm going to share this with everyone so that you can also study it another time. But all of the things here, I have more or less explained it. So then this is visualizing of one, you have what we call a confusion matrix where you visualize more. So, so, yeah. So when you run that, you now see that you have digits actually printed out. We also print out the confidence, whether it's correct prediction. We printed out the correct predictions and we printed out some of the wrong predictions. So like this one, the true value is 4, but the prediction is 9. Confidence is even high here. True value is 6, predictions. So uh, this is MNIST. What one thing you could do is try a better model than Lenet. Lenet was constrained because you could only do 2 layers. But now you can use multiple layers. You can then use a resonate. So one of the things you could try doing is use a resonate. Okay. So try this one. So that's it. Gone way, way, way beyond the time, but I'll stop here.